Hello guys, welcome to our YouTube channel. Today we shall be looking at graph-based acoustic modeling for pre-purchase vehicle inspection in Uganda. Our group code is SWAI Group 32, and our project involves keywords like large acoustic models, vehicle fault diagnostics, graph-based reasoning, synthetic audio generation, which includes diffusion and GANs. Then we have a repair and price estimation, and we have pre-purchase inspection tools. So we are three in our group, and our names are as you see below. And my name personally is Demovic Tayope, with my registration number and student number, as well as my email, as you can contact me with. Yeah, so giving a background about our project, we know that Uganda's growing second-hand car market mostly uses vehicles that are being used. So these vehicles are bought from abroad, but they come with different faults in them. So therefore, buyers face a high risk due to lack of reliable diagnostics to be carried out during the pre-purchase inspection. So expert mechanics are not always accessible, and inspections can be time-consuming. The sound from internal components like engines, brakes, transmissions, and others can reveal faults. So our AI is mainly based to automate the diagnostics from audio signals. So looking at the background and introduction, we have a simple block diagram which summarizes our project. As we can see here, saying that in this project, we focus on engine sounds from vehicles, detecting whether they are normal or faulty to ease repair and provide repair costs and final car price. This output is given based on processed data obtained from a dataset containing vehicle engine sound. Yeah, so we have our related works or the recent trends, which include acoustic fault detection models. So use the models like the CNNs, which is the convolutional neural networks, the AST for fault classification from engine sounds. And also carried out data augmentation, which is the process of expanding the data. For our project, we used engine sounds, so we expanded the data set using realistic audio transformations to improve generalizations and prevent overfitting, so that the data set is not biased towards either normal or abnormal sounds. We also used the knowledge graph based reasoning which links the fault types and the cause. So the knowledge graph links car models, engine sounds, and fault patterns to enhance diagnostic accuracy and contextual understanding of the model. Then we also have gap in localized deployment, where we have limited literature existing on deploying such models in low resource settings like Uganda, especially for mobile and offline use. Then the problem statement, the main problem, we see that buyers of second-hand cars in Uganda often lack reliable, accessible, and low-cost fault diagnostics, which risks them to overpriced purchases. So we see that the vehicles can come with faults in them. It may be including the engines, the braking systems, and other issues in the vehicle parts. So a customer may buy a used vehicle thinking that it is okay, only to realize that they have to spend more money on repairing this vehicle. Yeah, so the computational problem is that what we have to solve. So we have to develop a system that can process audio signals from vehicle parts and maps them to mechanical faults using transformer encoders and a structured knowledge graph. So here we shall focus on mainly engines that we shall process their audio signals to give us the mechanical fault that the vehicle has. Yeah, so in summary, we have the prediction and estimation of output, where we have the fault reports per part, repair cost, estimated adjusted resale price, and a few explanations with the evidence. Yeah, so research questions and objectives. We see the questions that came up, which include what acoustic features best capture vehicle component faults, and how can synthetic audio improve fault detection. So based on our project, we first came up with some questions to see how best we can implement it and what things are really necessary for this project. So after coming up with the questions, came up with the objectives that we want to achieve in our project. So the objectives include developing a graph-based large acoustic model, classify vehicle component sounds as normal or faulty, generating synthetic acoustic fault data using diffusion models and GANs to augment limited real-world datasets for better model training. Because our model had the few data, we had to augment them so that we reduce overfitting or underfitting of our model. Another objective was to integrate transformer-based acoustic features with a structured knowledge graph to provide explainable fault diagnostics and, and confidence scores. So apart from only generating the audios, we want to provide a report that gives detail to the customer or to the user or to the mechanic about the fault that has been detected in the vehicle. So we also derive and adjusted the purchase price of the vehicle that will be estimated after the fault has been detected. Yeah, so research contributions and outputs. We obtained the data set of different engine sounds, then we performed the explanatory data analysis on the data set, of which we generated different models, which include the CNN model, the GNN model, the graphical neural networks. We also have the AST model and the large language models as well on our project. Yeah, so looking at the methodology and system architecture, as I had said before, this block diagram summarizes most of it, whereby we have the audio capture and processing of our system. Then we follow by the feature extraction. So after the audio has been obtained, we extract the features that we need, of which we shall use it to implement the knowledge graph. Then we develop the models that are necessary. As I've listed them below, they include the CNN, the AST, and the GAN models. Then we shall finalize with the large language models that we need, and then finally get an output, which includes the reports, the cost, and the price, the final price. Yeah, so looking at the model architecture in the block diagram, summarizing that in CNNs, we treat audios as an image by converting them to Mel spectrograms, and these images, they use stacked blocks to detect hierarchical acoustic patterns followed by dense layers for classification. So crucial parts, we know CNN models, they'll use an input of Mel spectrograms uh, to split into a sequence of patch tokens. Then we shall have convolutional layers to identify spectral patterns, and we shall have a final softmax output for normal abnormal sounds, which classifies the different things as seen here in the block diagram, that we shall come to a final output after a series of classification of our information. Yeah, so we have the mathematical foundation, which includes a summary of the mathematical formulas used to come out with the classification, and also give us the Mel spectrograms that we shall need as our input. So following on to the next model, the AST model, it's a classification model that adapts to vision transformer architecture for the audio. So it treats the Mel spectrogram as a sequence of patches, which are then processed by standard transformer encoder to capture the different relationships and classifications. So we have the block diagram here, which simplifies our understanding, seeing that we also have an input needed of Mel spectrograms, and mathematical foundation can be seen. Then we go to the next model of the ENN, the graph neural networks that we used in our system, which also goes, it uses an input of graphs which have nodes that create the connection between uh, the different cores that we're using in our project. Yeah, so we also have the formulas that are used to generate this output. Then we have the large language model that we concluded with. As you can see, the necessary block diagram to summarize it, the mathematical formulas that were used, the input that is needed, of which most of this input we had it in our data set. Yeah, so moving on forward, we see a simple description of our dataset, which we obtained online because we found it hard to obtain different datasets of different mechanical parts. So the best part we got was for engines, which contained the 116 normal car sounds and 100 abnormal sounds. Yeah, so we carried out the EDA, the experimental data analysis, as you can see above. We extracted audio from our videos to get this output. You can see how the distribution is, which is not that bad, and to prevent overfitting. Yeah, this is a continuation of the EDF. Then we also see the CNN model that we were talking about previously. Uh, Here having the training and validation laws, then we have the confusion matrix of the CNN model, and seeing the accuracy of our model, which we obtained as 88.54. Then we also have the F1 score and the different uh, classifications of the normal and abnormal sounds. Yeah, even that of the AST model of the training that we carried out, the information is here. We obtained an accuracy of 87.58%, precision score, the recall score, and the F1 score, as well, also having the confusion matrix. Then also the integrated system, which will give us a sample of the output that we need, which will try to detect the location of the device, the cost of the part that will be the engine, an approximate cost of the labor, and the total cost that will take for the repair. Yeah, so we see also a summary of how it will estimate the value of the car, the final value after obtaining the repair cost. Yeah, so most of this summarizes what we have been explaining, the model selection and deployment, whereby we know how to use the knowledge graphs, the model selection, knowing the models we are going to use, deployment pipeline, how we are going to follow the development of the system through each model, then system integration pipeline, how we are going to integrate all these models together and finally deploy them. Yeah, system demonstration, as we have explained, that obtaining the engine data, uh, applying the advanced AI architecture, which includes the mail spectrograms that we used, structured diagnostic reports, as you have seen, providing the location, the repair cost, and others, and also having a user-friendly experience. Yeah, so in conclusion, the benefits that we obtained from our model is that we had an high accuracy, where the AST model achieved the high validation accuracy, which shows how good the system is. We also had an effective pre-processing because the audios that we used were from genuine sources, and the generated mail spectrograms that we used for capturing the engine acoustic patterns. Then deployment, we also successfully deployed our project, uh, which will be used for real-world problems by mechanics in order to ease the work of pre-purchase inspection. Yeah, we had the limitations, as I'd said below, that we faced the problem of getting data sets that contain the sounds of certain engine parts like alternators or brakes. So we mainly focused on engines. Yeah, so those are one of the limitations we faced. And also the other one, the solution to that had to be expanding the data set via synthetic augmentation that we carried out. Then the other problem that will be faced is noisy recording environments. So when you try to record the engine sound with a noisy environment around, it may be hard for the system to successfully generate what is required. The solution is to apply noise resilient pre-processing data and augmentation, which we did. Yeah, so that has been more our project summary. And thank you very much. Here are the references we used above, uh, the data set that we used, and some of the documents that we used to come up with our slides. Yeah, and we also acknowledge our supervisor, Dr. Marvin Galwango, for his guidance and the advice he provided to us. The feedback he always provided whenever I presented our project. Yeah, it has been so helpful. And we also thank his colleague Jim Jr., who helped us know about how to deploy our projects on different platforms. We also thank Hawaii Summit, whom we obtained the Engine Sounds dataset from online. Then a big thanks also to our group members who were able to uh, give us support to make this project a success. Yes, thank you all, and we shall meet next time. Yeah, see you.